Problem-solving skills are important in physics. In physics, we are given equations that represent real-life physical principles and are asked to use them to solve specific problems. Every problem comes with its own unique set of challenges, which is why it's important to develop analytical skills that can be applied in the event we run across an unusual or more challenging scenario. There is no one-size-fits-all solution to every problem, but there are some steps we can take to organize our problems in a way that gives us the best chance of solving them correctly. I'm going to use each of these steps to walk us through an example problem, which is going to be, if a person starting a foot race accelerates at 0.4 meters per second squared for 100 seconds, what is their final speed? Starting with step 1, which is, examine the situation and determine what physical principles are involved. This is where we pick apart the problem. What is the situation, and what physical principles are we dealing with? What equations apply to those principles? Pay attention to the variables involved, because if we're given directional quantities, called vectors, they require a positive and negative reference frame to determine if the vector quantity is going to be positive or negative in the equation. The reference frame is something we choose. It's usually not critical whether a vector quantity is represented as positive or negative. It just has to be consistent with our reference frame. A typical positive and negative orientation reads like a graph, with the upper y-axis and right x-axis as positive, and the lower y-axis and left x-axis as negative. If applicable to the problem type, we can draw a sketch for visual reference. In my opinion, this is more useful in two-dimensional kinematics and falling object equations, but it can also be useful for equations involving displacement and distance traveled. A question I'd like to leave for discussion purposes here is, what is an example of a one-dimensional kinematics problem scenario you would want to draw a reference sketch for? Now, one thing that's important to remember is that these equations are more than just numbers. They have to behave in a way that applies to the physical world, as in, yes, they are equations, but the equations dictate the way a real-world event takes place. The numerical solutions are meaningless if we don't keep this in mind. Now, in reference to our example problem, I've carried out step 1 by giving our vector quantities, which are acceleration and velocity, a positive starting point and direction. I've identified the physical principle involved to be Newton's second law of motion, and since we're given a constant acceleration value, a quick connection between the two would be to recognize that we can use kinematic equations for constant acceleration. I've also gathered a quick reference list for the kinematic equations for constant acceleration to reference when we analyze our variables. Step 2 is to determine what you know. Make a list of the values you're given. Identify all known information. Keep in mind again that some problems will refer to quantities in a certain way, one example being the word stopped indicating a velocity of 0. Also, initial velocity, time, and initial position are also generally 0 unless otherwise specified. With our example problem, we can list our known values. Acceleration is constant at 0.4 meters per second squared over a total time of 100 seconds. And since we weren't given an initial velocity, we can infer based on the default values for initial velocity that ours will be 0. Step 3 is to determine what values the problem is asking you to solve for. Making a list can help. We don't necessarily need a list because we're only asked to solve for one value, which is final velocity. Step 4 is to find an equation or set of equations that can help you solve the problem. Use your list of knowns and unknowns to determine which equation can solve for your unknown variables. If there's an equation that contains only one unknown variable, use it to solve for the unknown. There are times when there will be more than one unknown, and we might have to use a set of equations to find a solution. This is okay, we just have to take it in steps. Here's our list of equations that's been narrowed down to include only the equations which solve for velocity. And if we cross-examine our known variables with the equations, we can determine that this velocity equation leaves us with only one unknown, and we can substitute all our other known values in. Step 5 is to substitute the known values, accompanied by their units, into the equation selected in Step 4. When we substitute our known values into an equation, we can obtain numerical solutions, but the units are what translate these numerical solutions into physical solutions with real-world applicability. In our equation, we substitute in 0 for initial velocity and add it to the acceleration, which is 0.4 meters per second squared, multiplied by the time, 100 seconds, leaving us with a final velocity of 40 meters per second. Step 6 is to check to see if the answer is reasonable. We're meant to ask ourselves if the answer is reasonable, as in, does it make sense according to the circumstances? Is it realistic? This is classical physics, so we can more easily determine if a solution is reasonable based on what we observe in our day-to-day lives. To do this, we can check an answer's magnitude, sign, and units. For example, we found the final velocity of the runner to be 40 meters per second after accelerating at 0.4 meters per second squared for 100 seconds. The physics here is accurately stating what would take place under these conditions, but are these conditions and their derived solution realistic for our circumstances? Our circumstances involve a human accelerating at a constant rate over a set amount of time, and we have to figure out whether these conditions are realistic or reasonable for a human's natural capability. It's important that we make the connection between the solution to the equation and its real-world possibility. The goal of physics is to accurately describe nature, so we have to judge our solutions with reality in mind. There are some general steps to determine if a solution is reasonable. Step 1 would be what we've already accomplished. Solve the problem as normal. We solved it, our solution was a velocity of 40 meters per second, and now we can move on to step 2. Step 2 is it realistic? Make sure the sign and units are correct in our calculations, which they are, and ask, does the value seem accurate based on what is naturally possible? It's a bit difficult for us to put 40 meters per second into perspective, so we can convert it into miles per hour and reassess. 40 meters per second, convert those meters into feet per second, convert those feet into miles per second, convert that into miles per minute, and then convert into miles per hour. Now, an 89 mile per hour final velocity ran by a human. Is that reasonably possible? Clearly not. Step 3. If the answer is unreasonable, identify what could have created an unreasonable solution. Our answer was unreasonable, so what could be the cause for that? Inaccurate initial values, incorrect units, incorrect signs on our vector quantities, or mathematical errors are a few common causes of unreasonable solutions. In our example, after verifying that we didn't use incorrect values or units or make any calculation errors, we can make a couple possible assumptions for why what we came out with was an unreasonable solution by examining the variables we were given. The variables we had were initial velocity, which we know was 0, so that can't be a problem, but also acceleration and time. The only two places where this equation could have gone wrong is with acceleration and time. The acceleration could have been too large, or the time could have been too long. It might be possible for a human to accelerate at this rate for a shorter time, or it might be possible for a human to accelerate at a lesser rate for the given length of time. But together, it's not humanly possible. At this point, we can assume that the variables we have been given might have been given to us incorrectly.